No. Huh. You guys hardly ever have any questions about the homework. I'll just give harder homework problems or something. All right, let me hit the record button here. And there we go. Okay, so so last week yeah, it was last week. Whoop, here comes Anders. And then all right, so I sent out the answers to the test, and your answers didn't have to exactly match mine or anything like that. There's some flexibility in wording and all of that, but were there any questions about anything? All right.
I had one question about the one from the, I don't think you put the solution on the thing. It was the differential equations one.
Oh, yeah.
Whether, I don't know what, I just wanted to know what the answer was.
Well, wasn't that how long did you spend thinking about that?
I'm still thinking about it.
Yeah, that's why I don't put the answer up. I heard wonderful explanations for both decisions. No, it doesn't. Yes, it does. So yeah, I never give the answer out to that one. Just keep thinking about it. In the homework tonight, I throw one of those in there. So you'll see when you get the homework tonight, all right? So words really matter, don't they? That's how lawyers make their living. So keep thinking about it. You'll see in the homework tonight that, oh, okay, now I get it. So, all right, so we're working on this modular arithmetic stuff, which in essence is pretty simple, right? So we have, if A is congruent to B mod N, so everything in modular arithmetic is whole numbers, all integers, except N has to be bigger than 1. So N has to be 2, 3, 4, 5, 6, 7, and so on. A and B can be any integers, positive, negative, or 0. And here's another definition. So in essence, we can think of B as the remainder when A is divided by N. But that just gives us something called, oh, here comes Olivier. So often what we'll have is B will be the remainder after A has been divided by N. But B can be an infinite possible of numbers. We're always looking for the least positive one often. So here's another definition. So this is the modular arithmetic expression. But when we change that into quote unquote regular arithmetic, it just means A is B plus any. So here we go, Nate. So A is equal to B plus any or every multiple of N. How's that? So K can be any integer or K can be every integer, and this works. Is that a little hint about that one on the test? So this is a definition also, so if and only if. So I'm going to start out today showing you an application of modular arithmetic that's around us all the time. So we can think of a module as a cycle. So eventually you get right back to where you started from. So we looked at days of the week, we looked at months of the year. So I want to show you a pretty simple application that people have figured out. So when is this useful? So we're going to look at a 13-digit ISBN. And I'll show you where this comes up. So I'm going to pick one from this textbook here called Finite Math. And I'm going to write it down, assuming I can see it. So we have 978. Oh boy. Can't see this. Hang on. It's dark in here. Mirror you. Ah, there we go. That's better. 978 1 1 3 3 9 3 4 7 9 9 3 4 7 9 0. There we go. So this is a 13-digit ISBN, International Standard Book Numbering. So as I mentioned, oh, here comes Kenneth. Let me let Kenneth in, see if he's got any questions here. Hello, Kenneth, are you here? Hello, Kenneth?
Hi.
Oh, there. Okay. No, just wanted to make sure you were here. So you didn't really miss anything too much. So this is a different definition of modular arithmetic than I gave you last time.
Okay.
So I'm going to show an example of where this gets used. So 13-digit ISBN. So the first 12 digits are human created. This 978 is just a prefix that has no meaning.
Okay.
The first number is language, 0 and 1 are English. The next three numbers in this example are the publisher. This is the specific book. And it's this last number here where module arithmetic comes in. This last digit is called a check digit. It serves a function of error correction. So if you type in an incorrect ISBN, and 95% of errors when you're typing in a bunch of string of numbers, 95% of the errors involve one digit. And this will catch it if you did it. So I'm going to show you how this check digit, so the first 12 digits are created by humans. This last digit is created by a modular arithmetic algorithm. And it's wonderfully simple. It's elegantly simple. It's really lazy. So I want to show you how this works. 10-digit ISBNs work slightly differently, but for our purposes, it works. Let me click up. So here's how we begin. Starting from the right, we number these. We do 1, 3, 1, 3, 1, 3, 1, 3, 1, 3, 1, 3, 1. So starting from the right and 1, you just alternate 1s and 3s. So 1 and 3 are the smallest odd positive integers, so very lazy. This would work with other odd, sequential odd integers as well, but this is lazy. The next step is we multiply. So we get 9, 21, 8, 3, 1, 9. Let me do this one. 9, 3, 27, 1, 12, 7, 27. And here's sort of the genius of this. Now, this check digit has to be a single integer. So it can be anything from 0 to 9. But here's the key. No matter what this digit is, what do you get when you multiply by 1? You multiply anything by 1, you get back that number. This is called the identity. So 1 times anything is that anything. Okay, now we're going to add these numbers, but instead of adding the numbers like this, because we're likely to make a mistake, we're going to reduce all of these numbers mod 10. Let me use a different color here.
Professor?
Yeah, Zane.
Under, there's the 27 towards the middle there. 1 to the right, I believe you wrote 1 instead of 3.
Thank you. Thank
No
you.
problem.
You know what? I would have known in about a minute, I would have known I made a mistake somewhere. This is how the check digit works. I didn't do that on purpose, but what I'm about to do would turn out to be wrong, and that would tell me that there's a mistake somewhere up here. So this is a 3. Thank you for catching that. Arithmetic. Ugh. Okay. Now we're going to reduce all of those 13 numbers mod 10. Now, working mod 10 is easy. So whenever you divide a number by 10, the remainder is always that final digit. 11,943 divided by 10 leaves a remainder 3. 942 divided by 10 leaves a remainder of 2. So dividing by 10 The remainder is always that final digit, so it's easy. So we divide 9 by 10. 9 is smaller than 10, so the remainder is 9. 21 mod 10 is 1, because divide 21 by 10, you get a 1. This will be 8, this will be 3, this will be 1, this will be 9, this will be 3. 27 divided by 10 leaves a remainder of 7. 3 divided by 10 leaves a remainder of 3. 12 divided by 10, remainder of 2. 7, 7, and divide by 10, and you get 0. Now we add these numbers. Oh, this is the hard part, adding, right? So don't let me make a mistake. So 9 plus 1 is 10, 18, 21, 22, 31, 34, 51, 54, 56, 56 plus 7 is 63, plus 7 is 70, plus 0 is 70. So this adds up to 70. Now, here comes the modular arithmetic. This 70 is 0 mod 10. Now, when you have a, when b is equal to 0, if b is equal to 0, then a is equal to a multiple of the mod. So not mod 10. Anytime your congruence comes out to be 0, it just means this number is a multiple of 10. And that tells us for a 13-digit ISBN, that tells us the check digit and this little method always has to give you a multiple of 10. So that means that doesn't mean the check digit is true. It means that it's valid. Now remember, valid and true are very different. If you come up with a 0 mod 10 at the end of this little process, that means a system will accept that ISBN as being valid. It could still be wrong though. You could have mistyped a couple of numbers up here that still result in 0 mod 10. So your ISBN can be incorrect, but the method shows that it's valid. So big difference between valid and true. So this is how the ISBN system works. When you go through this pretty simple thing, 131313131313, and you come down to 0 mod 10, you have a valid ISBN. Still could be incorrect, but it's valid. So it's pretty simple, right? We did this by hand. So when you're typing something in, you know, this algorithm happens basically before your finger's even off the enter button on here. So let's try another one. Unless there's a question here yet. Everybody kind of okay? I think she puts this in this book. She never used to, but it's included in the edition that I uploaded for you. So let's try another one. I'm just going to leave that right there.
Professor, I have a question.
Yeah, Michaela.
It's like one from like the homework, but I'm just wondering, like, how does it work when you like mod with like negative numbers?
You mean one of these numbers being negative?
No, like if it's like 1 mod 6 equals like negative 59 was like the one from the book.
Oh, because yeah, that's possible. So A and B can be any integer, positive, near 0, or now n has to be positive. So that just means in terms of, well, let me do one more example,
Okay.
and then I'll get to your question, all right?
Okay.
But the quick answer is, if we were thinking of what day is it 900 days from today, but if you wanted to say what day was it, if you go backwards, you see you'd come up with a negative number.
Yeah.
Yeah, so that's an example. That's an example of where negative is. So today is Monday. So we declare Monday is 0, then yesterday would be -1, one day backwards.
I see. Okay.
Yeah, I'll show you in just a minute though.
Okay. Thank you.
Yep. Let me see. Let me pull up another. Oh, geez, I got to turn this on again. Hang on. Okay, here's our next ISBN. So we are nine, seven, eight. So most of the books you see are going to start with 978, but there is I think I've seen 988 before because we're running out of numbers. So 978, 0, 1, 3. So 0 means English. 0, 1, 3, 4, 6, 8, 3, 4, 1. 4, 6, 8, 3, 4, 1. And then the check digit here is a 6. Okay, so now I know this is a valid number. I know it's a correct number because it's on the book here, but let's go through our little process again. So we multiply, so 9, 21, 8, 0, 1, 9, 4, 18, 8, 9, 4, 3, and 1 times the check digit gives me the check digit. So it's a wonderful system, very lazy, very easy. Now we multiply these numbers. I'm sorry, reduce. You could add up all of these numbers. You could do that. And as long as it added up to a multiple of 10, this number would be valid. So if you if you add all these numbers up and the total ends in a 0, you're good to go. However, I don't know. Adding those numbers up, you're likely to maybe make a mistake on here. So reducing mod 10 makes the addition easier. So reduce mod 10. Anytime A is less than N, this is always going to be an A over here. So we have 9, 21 divided by 10 leaves a remainder of 1, 8, 0, 1, 9, 4. 18 divided by 10 leaves a remainder of 8. Then we get 8, 9, 4, 3, 6. Well, that didn't help a whole lot, but oh well. Now we add, oh man, 18, 19, 28, 32, 40, 48. 48 plus 9 is 57, 61. 64 plus 6 is 0. So by coincidence, oh, that's a total coincidence. We got 70 again. And 70 is a multiple of 10. You can read this in English as this number is equivalent to 0 mod 10, or this number is a multiple of 10. So that check digit works out, which we know that it did because it's from a book. So pretty simple scheme for having an error correction system. And this actually saves lots of money. Let me give you a little example. So suppose you work for a college bookstore and you need to order 500 copies of this book. And let's say the college is somewhere in New Jersey, and the publisher's warehouse is somewhere in Tennessee. So you go online and you go to their online ordering system and you say, I need 500 editions of this book, and you type in the ISBN number and you type it in incorrectly and the system accepts it. So somebody at the warehouse gets paid to put 500 books on a truck. Somebody gets paid to drive the truck all the way to New Jersey. Somebody gets paid to take the books off the truck in New Jersey. Somebody gets paid to open up the box and go, crap, these are the wrong books. So now you got to spend all that money sending all those books back, and then you got to pay all that money again to have the right books shipped in. Thousands of dollars, right? So if you make a mistake when you're typing in the book order and you type a number in wrong, it'll come back and say error, invalid, not incorrect ISBN. It'll say invalid ISBN. You check your work again. Oh, geez, I typed a 3 here instead of a 4. So this helps correct over 90% of type-in errors on there. And it's a pretty simple scheme, right? So UPC codes, UPCs work the same way, the little barcodes here. 10-digit credit card numbers have their own error correcting schemes, also based on modular arithmetic. They all have different schemes. The driver's license has a check digit corrected in there. So we have this sort of simple idea of modular arithmetic. Divide this number by this number, and this is the remainder. So just a little application on there. Okay, so Michaela asked about negative numbers. So let's take a look at a negative number. Which homework problem was it, Michaela? Number, I forgot what you said.
It was 8 B. I don't know, sorry, 8C.
Oops, 8C. Oh, crap. Hold on a minute here. Page 386. This digital book has such a sensitive trigger on it when you're trying to find something. 8, there it is. Okay, so 8C. Oops. 8C. 8C is verify. So when the homework says verify, you know the answer is true, and you have to come up with correct. There was one problem in there that says which ones are true or false, and then you're not sure if you made an arithmetic mistake or something. So we have 45 minus 104, and they want you to verify that that is 3 minus 2 mod 6. I don't know why she has the mod 6 in parentheses, but anyhow. Okay, so 45 minus 104 comes out to be what? So 3 minus 2 is negative 1. And 45 minus 104 is, negative 59. Did I do that arithmetic correctly?
Yes.
I'm sorry, what? Oh.
Yes, that's right.
Okay, so negative 59. So let's look at this. So we can have 6 goes into negative 59. Now we can ignore the negative here. So 6 goes into 59, how many times?
9 times.
9 times. So 6 times, 9 times 6 is 54. Then we subtract, this leaves me with a 5. Oops. Okay, so that leaves me with a remainder of 5, right? Well, negative 5, actually. So let's take a look at this. So is that correct? Well, so we have this remainder here. So the answer is yes, because what happens here, this number is not unique. There are an infinite number of correct values here that make this work. So let's go back to my little Monday example. So today is Monday. So we have Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. So 0, 1, 2, 3, 4, 5, 6. But if I count backwards, I could say negative 1, negative 2, negative 3, negative 4, negative 5, whoops, negative 6. So you see, you can think of a negative number as direction going backwards. Did I do that right? Yeah, I did. So negative 3 and positive 3 both relate to the same day if we're starting from Monday here. Does that help explain that a little bit? Oops, Michaela? Hello? Uh-oh. I think Michaela, are you there? sorry, you're down in the chat room. Sorry, I didn't see it. Yeah, so negative numbers, it doesn't have to be direction, but that's a nice way to think of negative. So if you've had vectors and things before, if you have a positive vector, a negative vector just means go in the other direction. So all of this is connected here. Okay, so let's do a couple of other things with modular arithmetic here. All right, so how do we prove things using modular arithmetic? So without context here. So I'm going to show you how to do a couple of proofs in modular arithmetic. And these proofs are not word proofs. These are going to be what I consider arithmetic proofs. You just calculate things. So math is all about patterns. So it's all about patterns. So let's say that we have, so let's say that 15 is congruent to 4 mod 11. Okay, well, that's just true. 11 goes into 15 once and the remainder is 4. And let's say we also have that, 22, whoops, 27 is congruent to 5, wait, 27 to 5, yeah. Okay. So because of this, we know that 15 plus 27 is congruent to 4 plus 5, 11. So one of the homework problems was kind of like this. So is this true? Well, 15 plus 27 is going to be 30, 42 is congruent to, whoops, 9, 11. So is that true? Well, 11 goes into 42 3 times and leaves a remainder of 9. So this is true. So we have sort of a pattern here. So we can add these numbers together and then consider what it is mod 11. Or what we see is 15 mod 11 is congruent, whoops, 15 mod 11 plus 27 mod 11 is equal to 4 plus 5. So the reason for this is instead of adding two big numbers together first and then reducing mod 11, you can reduce them each separately to begin with and then add the answers together. And why is that important? That saves processing time. Human processing time, instead of adding, now these aren't big numbers, but if these were really big numbers, instead of adding those together and then going through the tedium of dividing by this, you can reduce them each separately first. And that makes not only human arithmetic easier, it makes for faster processing time in a computer. So the pattern here is this. So prove if A, oh, I don't want to use A. Well, why not? If A is congruent to B mod n, and I'm going to change this a little bit. If A is congruent to D mod n, and B is congruent, and B is congruent to D mod n. The reason I'm using A, C, and B, D here is that matches the homework that's coming. So prove then A plus B is congruent to C, A plus B is congruent to C plus D mod N. So we're gonna compute that and show how to prove that. So premise, A is congruent to C mod N and B is congruent to D mod N, then prove that adding these two numbers together will be the same thing as adding these two numbers mod N. So here's how we prove. We use the definition. So if AC mod N, then A is equal to C plus KN. And everything here is integers. That's just a definition. We also know that B congruent to D mod N, that means that B is equal to D plus, now I can't use K. I have to use another integer here, so I'm just gonna say J. So this is definition. Definitions are always true because they're definitions, right? So we know that's true because that's a definition of this expression. So if we add A plus B together, now, so A plus B is equal to, whoops. Now I'm using an equal sign. So now I'm into regular arithmetic. By direct substitution, this becomes A plus KN plus D plus JN. I want to just pause there. Everybody see what I'm doing? We're given this is true. That's a premise. It's true. And we want to conclude, we want our argument to conclude this.
Professor, you wrote A plus B equals A plus KN. I think that's supposed to be C plus KN.
Oh, you're right. Good thing you're paying attention. Thank you.
No problem.
Yeah, so I'm kind of, yeah. So the letters are confusing, but I'm making this match what's in your homework tonight. So we know that this is true. Then by definition, A is this number plus this. So this tells me that if I divide A by N, this will be my remainder. Now we use regular arithmetic. We can use the property of commutativity. I can rearrange this because it's all plus signs. And now in these last two terms, I can factor out the N. Oh, I'm running out of room here. So all I did was factor out the common factor of N from the last two terms. And here's something that we're allowed to assume as true. K and J are both integers. If you add two integers together, what do you get?
Another integer.
You get another integer. So I'm going to have to erase this here a little bit because I'm running out of room. So we can assume without proving it that an integer plus an integer is an integer. So this now gives me A plus B is equal to C plus D plus, so I'm going to say that K plus J is another integer. And I'll just use S. So, whoops. So I'm going to say that K plus J is equal to S. Integer plus integer is integer. Well, this proves it because Remember what QED means? Did we do that at some point in this semester? Did I do QED before? Can't remember if I told you this or not. Have I done this?
I don't think so.
Oh, there must have been a different course. So QED is the abbreviation of a Latin expression that says quo erat demonstratum. It means thus it is shown. It kind of means ta-da, end of proof. So beginning with this, by definition, if you have a number plus a multiple of n equals a, then by definition, this says C plus D mod n. This is a definition going this way. So we've proved what we need to prove. The sum of these two numbers, mod n, is equal to the sum of those two numbers, mod n. So big numbers can be added together first and then do the mod, or you can do the mod first and then add them together. So that's an example of an arithmetic proof. So I should have turned the board this way. And then I could have done that. I never thought about that before. But anyhow, question on that?
I have a question on it.
Okay.
So that final step, there's an equal sign. Look
sorry.
at the definition. What? All right, yeah. I was just curious if it would be congruent or equal.
No, that's just me not paying attention. Yeah.
Okay, thank you.
Anytime you have an equal sign, you can always put the third bar on there because, but you can't take an equivalent sign away, but you can always put one in there. It's always correct to use 3-bar equal, but it's not always correct to replace this with a 2-bar equal. And that goes back to the question on that test, what's the difference between equal and equivalent, right? That's a very important subtlety. And as long as you brought that up, Zane. That's true. So is that. So when you're using inequalities, you can always have the or equal because this is an or statement. But in this case, you can't always take this away, but you can always have it there because of the or. So anytime you have an equal sign, you can always add that third bar, but you can't always take those away. So that's the important difference between those two. All right, let's try another one of these. So you got some of these in the homework tonight. Let me see, what else do I want to do here? Hang on a minute. Yeah, let's try this one. So let's look at 2 mod 9. Well, whenever A is less than the mod, A is always congruent to itself because 9 goes into 2 0 times and the remainder is 2. But there's an infinite number of answers here.
Can you repeat what you just said? You said whenever A is less than the mod, then what?
Oh, hang on a minute.
Yeah.
That's what I said. That makes sense?
Yes.
Yeah, so if A is smaller than the n, then n doesn't go into A, and A is the remainder that's left over. But what happens here so all of these are true, right? So 9 goes into 29 3 times, remainder 2. 9 goes into 22 times, remainder 2. 9 goes into 11 once, remainder 2. 9 doesn't go into 2, remainder 2. And so, Michaela, how am I going from here to here to here? This is a question for you, Michaela. What am I doing from here to here to here to here? Where's Michaela? Michaela. Oh, maybe she went to get coffee or something like that. Michaela, are you there? Oh, so what am I doing from here to here to here? So from 2 to 11, from 11 to 20, from 20 to 29, what am I doing? No, this is the number I'm dividing by. I'm dividing by 9. I'm changing, you can think of the remainder. Do you see what I'm adding here every time? So 2 plus 9, 11 plus 9, 20 plus 9. And I'm getting the same result every time? Yes. What happens if I go that way, Michaela? The pattern continues. So 29, subtract 9, 20, subtract 9, 11, subtract 9, 2, subtract 9. What would I have here? If I go the other way, you see what happens? There's your negative number. And then if I went again, and there's another way of looking at that negative number that you had asked me about earlier. Now, here's something to notice with the negative numbers. If you ignore the negative numbers, 2 plus 7 is 9. 2 plus 16 is 18, which is a multiple of 9. So here's another example of where those negative signs come in. So this list would be infinitely long in both directions. And it's the fact that in the world of Mod 9, we can represent the number 2 an infinite number of different ways, and that's what makes encryption schemes work. Because we're going to be looking at encryption schemes at some point in the near future here. Okay, now I want to do something else with this. So that's just a little pattern to look at with mod. So it's nice to think of modular arithmetic as a clock, round and round and round, and you never leave that clock. So no matter what time of day it is, in exactly 12 hours, you will be right back at the same number. In 24 hours, you'll be back at the same time with the correct AM and PM. So modular arithmetic, you can just think of cycles. I want to show you something else that happens here. So 2 is congruent to 2 mod 9. 2 squared is congruent to 4 mod 9. 2 cubed is congruent to 8 mod 9. 2 to the 4th, well, 2 to the 4th, 2 to the 4th is 16. 9 goes into 16 once and leaves a remainder of what? So what's 2 to the 4th mod 9? What number goes here? I'm looking now for the smallest positive number here. I'm looking for the residue. So 2 to the 4th is? Nope, not 2. 2 to the 1st is 2. 2 squared is 4. 2 cubed is 8. 2 to the 14th is? Well, 2 to the 14th is 16, but we're in mod 9. So what is 16 mod 9? And this is anybody, not just you, Michaela, but. So 9 goes into 16 once and leaves what as a remainder?
7.
Seven. Very good. That was a hard question, wasn't it? 2 to the 5th is what, mod 9? So 2 to the 5th, 2 to the 5th is 32, but 32 mod 9 is what?
5.
5. Okay. 2 to the 6th, 2 to the 6th is 64. What's that, mod 9? Two to the 5th, or sorry, 2 to the 6th is 64. So 9 into 64, and the remainder is
1.
1. So 2 to the 7th, without even thinking about it, what's 2 to the 7th? Don't even need to think about that, really. Well, or maybe. What's 2 to the 7th? 2 to the 7th is 2. 2 to the 8th is 4. 2 to the 9th is 8. 2 to the 10th is 7. 2 to the 11th is 5. 2 to the 12th is 1. 2 to the 13th, so we're at 1. So 2 to the 13th, it starts all over again. So exponentiation also is cyclical here, because think about it this way. Two to the 7th is equal to 2 to the 7th is equal to 2 to the 6th times 2. But in mod 9, 2 to the 6th is 1, and 1 times 2 is 2. So by breaking up exponents, I can reduce things back down. So even with x, I'm taking the same element from mod 9. So in the mod 9 world, when we're working mod 9, the residues of mod 9, and residues again is the smallest set of non-negative integers that exist. So residues. So when you divide anything by 9, 0 through 8 are the only remainders you can get. You can think of residues as the remainder when dividing by 9. So if we keep taking this, if we say, let's take 5. So 5 is congruent to 5 mod 9. 5 squared, well, 5 squared is 25. So 9 goes into 25 2 times and leaves me with 7. Right? 9 goes, so 18, so that's 7. I think I did that arithmetic correctly. 5 cubed, well, 5 cubed is 125. If we do 9 into 125, that's 1, that's 9, that's 35. 9 goes into 35 3 times, that's 27. So 7, 8, 9, 10, 5. That would be 8 mod 9. Five to the 4th. 5 to the 4th is 625. And we divide 625 by 9. That gives me 6, that's 54. 85. 8, that's 72. No, wait, that's wrong. Oh, yeah, 9, that's 81, that's 4. So that's 4 mod 9. Five to the fifth is 2 mod 9. Oh, I just did 5 to the fifth in my head. 5 to the fifth is 5 to the fourth times 5, right? So 5 to the fifth is 625 times 5. That's a big number. But in mod 9, 5 to the fourth is 4. So mod 9, I can think of 5 to the fourth as being congruent to, 5 to the fifth as being congruent to 5 to the fourth times 5 mod 9. So 5 to the fifth is 4 times 5 mod 9. So 5 to the fifth, 5 times 4 is 20, and that leaves a remainder of 2 mod 9. So let me just pause there and see if anybody's got a question about what I'm doing here. I'm breaking big numbers down by doing the mod reduction first. And now I know that 5 to the sixth, well, in mod 9 world, 5 to the sixth is equal to 5 to the fifth times 5, but working mod 9, 5 to the sixth is congruent to 5 to the fifth times 5 mod 9. So 5 to the sixth is congruent to 5 to the fifth is 2. So 5 to the sixth, 2 times 5, 10 is 1 mod 9. Now, because I've hit a 1, and you will always get to a 1, always by this method. Now 5 to the seventh starts all over again, because 5 to the seventh is 5 to the sixth times 5. So now, using this, we start all over again. So here's where that mod that some of you knew the other day when I said percent sign, you knew mod. Now we can look at what is 5 to the 148th power mod 9. So 5 to the 148th power is a pretty big number, but we want to reduce that mod 9. I know it has to be one of these numbers because that's all there is. So 5 to the sixth gives me a 1. So I want to break 148 down. So we divide 148, that's 2, that's 12, that's 28, that's 4, 24. That gives me a remainder of 4. So 148, so 5 to the 148, I can think of equals, now this is an equal sign, is 5 to the 24th to the 6th power times 5 to the 4th. So I'm going to pause right there, and if anybody has a question about what I'm doing. I broke 148. So 148 is, oh, and for computer science, so this is the mod, and the top number here is div for you computer science folks. So 148 is 6 times 24 plus 4. So when you raise an exponent to an exponent, you multiply. So 148 is 24 times 6 plus 4. So now I can break this down. I can rewrite this as using commutativity. In regular algebra, commutativity, A times B is equal to B times A. So I can say 5 to the 148 power is equal to 5 to the 6th power plus 24. I'm just switching those times 5 to the 4th. So 5 to the 148 power is congruent to 5 to the 6th to the 24th power times 5 to the 4th mod 9. So 5 to the 148th power, 5 to the 6th is 1. So this is just 1 times 5 to the 4th mod 9. So 5 to the 148 power is, and 5 to the 4th is 4. So 4 mod 9. So in the mod 9 world, 5 to the power 148 takes you right back to the residue of 4 in mod 9. So it's a bunch of arithmetic, but this makes everything run much, 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 much faster. And when you're processing anything, it's all about get to the answer first.
So are you trying, is the goal for this to try to get to whatever equals 1 so that you can, like, you know how we ended up with where you replaced 5 to the 6th, that's now 1. Is that the goal, to get it to a 1? So,
well, it's not so much a goal, it's a consequence of doing exponents in the mod world. If you take any residue, well, it doesn't even have to be a residue. If you take any number at all, mod 9, you can take 8,342 to the first, 8,342 to the second. Eventually, you're going to get to an exponent that takes you back to 1. You have to get there. Well, actually, you don't have to get there. 9 is not prime, but 9 is what?
odd.
Yeah, odd. But even more importantly, 9 and 5 have no common factors. The residues have no common factors with the modulus. If you take a multiple of 9 to any exponent is going to be 0. It's always going to be a multiple of 9, right? So Nate, not so much the goal. This is an example of what happens in the mod world and how you can break down a huge number in mod 9 by using the cyclical nature of the modular pattern. So goal, yeah, that was the goal here, to get to a 1, and that makes, you can break these things down much easier.
That makes sense.
Yeah. Yeah, that's why it's in a textbook. It all makes sense. So this is a bunch of arithmetic, but this brings back, so you saw it today, sort of a cute little example of how ISBNs have that check digit using a mod of 10. 10-digit ISBNs, which aren't used anymore, they have a different scheme involving mod 11. Some textbooks have the 13-digit and the 10-digit ISBN printed on them, but that's because when they first came out, there was only 10-digit ISBNs. And then when they modified the books, they just put 978 in front of the number and changed the check digit on there. Brand new books tend to only have 13 digits. So that's just sort of an example of where mod gets used. And now we're getting a little more into, we're looking for patterns and how do we make things easier. All right, questions about anything? All right, so I'll put up some homework for this. There's a couple of proofy things on there. And to do the proofy things, you use the definition like I used. And then there's a couple of examples of doing this. And I'm not sure where we're going yet on Thursday. Eventually, we're going to look at some secret codes. We might do some secret code writing on Thursday. Let's see what my mood is. Has anybody got any questions, comments, or anything before we say sayonara? No, all right, let me stop the recording here. So I'll get this up. And there we go. I guess I'll see you all on Thursday. So ta-ta for now.
Have a nice day, Professor.
Thanks. And
Have a nice day.
Zane and everybody, thank you for catching my arithmetic mistakes. I really appreciate that. Bye.
Take
Have a
care.
great day, Professor. Take care.
See ya.
Have a good day.
Bye, everyone.
Have a nice day.